And if eventually you get to the end, and this is all x's, this is all x's, and there's no further symbols here, so that the length are the same, and all the symbols, the corresponding positions, they're all the same, then success, then you go to accept. Now to get all those details and put them in terms of state diagram and all the transition rules and so on, so you've got to give this a lot of thought, right? It's non-trivial, a lot of details, as I keep emphasizing. So, and this is only half the story in a sense. So I suspect probably there'll be other states to fill this up to 14, maybe, or maybe it's an error. This is not the whole story, even in terms of the state diagram, because if this is not an error, then there's six ordinary states missing, and the reject state also missing on this diagram. Okay. All right. Right. So we've done that effectively. Obviously I've skipped over a lot of details, but they're just too many. Now that's the whole point of why full descriptions, full formal descriptions of Turing machines are rarely given, right? For that reason. But I hope you've got enough to to figure out what's going on here. With this sort of read, check it, same, okay, go back, read the next one, come back again, check it, is it the same, okay, read back, and progressively you're Xing, step by step, symbol by symbol. This is your next non-X, well, you'd move to here, and so on. So remove, until there's nothing left. Okay, that's how you show the two strings are the same. They're the same W. Now, with that in mind, you think this through. Think it through at low level, a transition from one state to another at that very low level. And think of the more global strategy. Why do you have this diagram structured this way? To do what? Okay, so a nice intellectual brain teaser for you, and get accustomed to doing this, because you will there'll be quite a few Turing machine design exercises at the end of the chapter when the time comes for you to get into the problem solving part, which is more demanding. You have to design a machine, a Turing machine, with several of them. All right. Next example, our third. Now we'll have four before we move on to another major topic, which is, by the way, just a minute. I think it's alternatives. Let me just check. So, then we get into another section. It'll be the second section of the chapter. So 3.2. Variants, A-N-T-S, so the noun. So in other words, variations of Turing machines. For example, more than one tape. Does he talk about infinite tapes both ways? Seems not. I don't see any figures, diagrams with tapes both ways. Strange, different, quirky compared to other authors. Okay, third example. So in the text 3.11. Now this time, interestingly, this example has several features. One is it does a bit of arithmetic. Okay, it actually handles multiplication of integers, positive integers. And so that's interesting. So a bit of arithmetic coming in. And the other thing is part of this Turing machine behaves like a finite automaton. In other words, it just totally ignores the stack. Right? It's not reading or writing on the stack, just ignores it for a while. Like the processing, the computation of a Turing machine, you can often divide into stages. or phases, or whatever you want to call it. So during a particular stage, let's say, it's doing one kind of subtask, and then the next stage of its computation, it's doing a different subtask, and so on. So one of the, you'll see in a moment, well, next session, one of the stages of the computation of this Turing machine, N3, next one, is it's acting like a finite automaton. In other words, finite automata do not have, not stacks, I was going to say stacks, they don't have tapes, right? They're just effectively ignoring what's on the tape. Well, they're not, well, in the sense they're not, I better be careful here, they're not writing onto the tape. I mean, they are reading, because if you're moving, you need to know where you're going and when to stop moving and stuff like that. So it's reading effectively, but it's not writing. In that sense, it's ignoring the tape. So in that sense, it's behaving a bit like, well, no, it is behaving like a finite automaton because a finite automaton does read its input, right? So in that sense, it is behaving as a finite automaton, right? But it's not writing onto the tape. A finite automaton does not write onto the symbols in its input stream, right? It only reads them. So this Turing machine, in one of its stages, will behave like a finite automaton, which is interesting. All right. So what's the task? What's the language? Now again, this machine will be a decider. Okay. It will. The only ways it can stop to be in the reject state or the accept state. Right. There's no looping. It's a decider, and the strings in this language C, big C, are of this form. So you have 3 symbols in your string alphabet, little a, little b, little c, and a string in that language, C, has the following form, that these are positive integers here, so I, j and k are, take that back, I, j and k are greater or equal to 1, not 0, 1, okay? I, j and k are greater or equal to 1, right? So this string belongs to the language if it has the property that these powers here, so you'll have IAs followed by JBs followed by KCs. Right? That's what's meant by these powers in a sense. These are not mathematical powers, they're more like repetition numbers. The instructions, it's shorthand for saying you have IAs in your substring and JBs in the substring and KCs in the substring. And the whole string belongs to the language if I times j equals k. Right? I times j equals k. Okay, so this language is doing a bit of arithmetic in the sense of multiplication of positive numbers. All right. So again, we'll start with high-level strategy at first, give you an overview of the task. Well, we know what the task is, the overview of the strategy of how to do it, how to see whether an input string is of this form that obeys this description. Here's your condition that the IJK have to obey for this string to belong to that language, for this string to belong to the set. Alright, so like here's a stage, if you like, example of a stage. So first task is, now you'll start now the first A here will be by Sipser's way of doing things, which I find odd. Put this first A in the leftmost square. Right? Sipser's tape is only like half an infinite tape. Alright, so start there and then just scan right across to the end of the string, and you'll know when it's at the end of the string because you'll meet your first blank. Okay? Alright, and check that as you scan across, that your string is of this form, that it is, all A's and then all B's and then all C's, so that you don't have like A's mixed up in the B's or B's mixed up in the C's or nothing like that. Right? So you in a sense, your first stage is to check that your string is of this form, A star, B star, C star. Right? No mixing. So you have a block of A's followed by a block of B's followed by a block of C's, and if you don't have that, reject. Right? So you do an initial scan to throw away all those strings that are not of this form, A star, B star, C star. Okay, so that's your stage one. So if the string that you're scanning, the M3, the machine is scanning, is not of that form, then reject. Okay, and only so that leaves then the strings that are of this form, and then you need to check that I times j is equal to k, and then you can ask yourself the interesting question: well, how on earth would I do that? Right? Imagine you're the designer. So try and think of a global strategy, an idea, an essential kernel idea that would allow you, using a Turing machine, to check if I times j equals k. How would you do that? In fact, just for fun, I suggest, before you do look at the next session, have a go at it yourself. Try have the essential idea. How would you get a Turing machine to do that? Not the details, just the broad idea. How would you go about checking that I times j equals k? Given that you've got IA's followed by JB's followed by KC's in your string, a block of A's, a block of B's, and a block of C's. How would you get a Turing machine to check that I times j equals k? Interesting question.